So sum of Poisson random variables, it's very useful when we deal with Poisson processes and in other applications. Luckily, the sum of Poisson random variables end up being something very simple. I'm not going to write what that is yet. So suppose W is equal to X plus Y, where X is Poisson lambda 1, and assuming T to be equal to 1, going back with the lambda T notation, and X2 is Poisson lambda 2. With like, oh, thank you. I'm going with X1, X2. Should we keep it as XY or X1, X2, which is easier? Or does it matter? Huh? It's, yeah, this is good enough, right? So I like to write it as X1, X2, but it's okay. Now we have to find the distribution of W. So what is the probability of W? That would equal to the probability of X plus Y equals W. Agreed? Well, I can write this as probability X is equal to W minus Y. So far, so good, right? But W is a random variable. Excuse me. Uppercase Y is a random variable. W is some outcome. So what are the possible values for the random variable W? It is the sum of two Poissons. What is the support of X? Huh? 1 through 10. 0 to infinity. So that said, what is the support for W? 0 to infinity. So W is just a number from the support, and X is a random variable, Y is a random variable. So I can't just plug in little y here or lowercase y here and use the PMF of Poisson. I've got to do something. What is that something? So we have X is equal to W minus Y. And conditioning on Y, on all possible values for Y, which would be from 0 all the way to infinity, and W minus Y. We can't just condition and not do other things. So probability of Y equals K. Law of total probability, I'm simply taking the random variable X and putting it on the partition of Y. This part is a rule. What rule is that? What? Right, entire thing, but just this part. Base rule? Base rule. Thank you. Multiplication rule of dependent events. So lambda, we know the probability of X equals X is lambda raised X e raised minus lambda divided by lambda factorial. Standard Poisson distribution. So x is 0, 1, 2, all the way up to infinity. In this case, since I've defined x to be Poisson lambda 1, I'm going to replace lambda in our usual notation to lambda 1 because I've changed the rate from lambda, which is what we did last time, to lambda 1. For probability y equals y, all I have to do is change x to y, lambda 1 to lambda 2, and we're done. Is there a one? What? Oh, sorry. Way too excited about lambda 1 for some reason. So since I've conditioned on y, and that is equal to k, I can write it as w minus k because individual values of k. E raised minus lambda 1 divided by w minus k. That's all. Multiplied by probability of y equals k, which is lambda 2 raised k, e raised minus lambda 2, divided by k factorial. This is a probability that w equals little w. Why would that be? What? You said have probability was w. Oh, right. Give total probability. Zero to infinity. Well, that's a constant. That's a constant. I can pull those out. Good. Yes.
And the second part on the probability that W comes from the probability that life is K, right?
Yes. That's why we condition. We condition so that we convert the random variable to a single value. We can't just, randomly convert y equals some single value, which is why we use the law of total probability to condition on individual values of y. So that would give us we got this far. What do we do? Without messing up algebra. I need a w factorial there. How do I come up with that w factorial? That's a big, easy question.
W factorial over W factorial.
Thank you. So e raised minus lambda 1 plus lambda 2. The W factorial does not depend on the sum or the other way around. So probability of W equals W. E raised is equal to E raised negative lambda 1 plus lambda 2 divided by W factorial. Sum k equals 0 to infinity. W choose k. Lambda 1 raised W minus k multiplied by lambda 2 raised k. And what would that sum equal to? One. Why? Lambda 1 is not a probability. And lambda 1 is not equal to lambda 2. I see where you're getting from negative lambda 1. Or excuse me, lambda 2 is not 1 minus lambda 1. Nathan, you're the one who said it's close to the binomial theorem.
So we can definitely change it from k equals 0 to W, because anything past W just gets 0. So, there's another clever trick.
If you use binomial theorem, it's just the reverse of what we have. For example, a plus b whole cubed is a cubed plus 3a squared b plus 3ab squared plus b cubed, same argument. So what we have is lambda 1 plus lambda 2 raised to w. I went from here to there because of binomial theorem. Now raise this out. Of course, we are making an important assumption that x and y are independent, right? Otherwise, this is not going to work. We're able to condition on a single number, use law of total probability directly, because x and y are independent. What does that look like? I am going to say that that is a known distribution. That is something we know, that it follows a distribution that we know. So this is nothing but a Poisson bounded variable. If I call lambda 1 plus lambda 2 as say x, then that would just reduce to e raised negative, well, I shouldn't use x. Just lambda, how about that, lambda? E raised minus lambda, lambda raised w divided by w factorial. what does it look like? That looks like the PMF of a Poisson. So what did we conclude? We simply concluded if x1 and x2 are independent Poisson random variables, they don't have to be identical. If we sum them together, the result is Poisson with rate lambda 1 plus lambda 2. So all of this would work provided x and y are what? Independent. Now, what if suppose U is sum I equals 1 to n xi, where xi is Poisson lambda I, then U is wait. X U is also Poisson, but what is its parameter?
The sum of blank eyes.
Good. Provided. Can I call xi's to be identical in that case? In this scenario, if I define xi as Poisson lambda I, are they identical? They certainly are independent. Could I say that they're identical also? The lambdas are different, so they're not identical. If all lambdas were the same, then they are independent as well as identically distributed. Okay, so I hope you may wonder why I picked salmon, because I woke up this morning and I had a craving. No, I just had a craving, so I haven't fixed my craving yet. So we do know, I hope you guys know, salmon typically swim upstream to spawn. So the number of salmon that can swim upstream in 3 rivers, one is A, B, and C. The first case, it's 10 per hour, so 10 of them would jump. And in the other case, other 2 rivers, it's 8 and 16. We want to find the probability that exactly 20 salmon swim upstream in river A per hour. Do we expect that probability to be high or low?
Pretty low.
Pretty low. Why is that? The rate is 10 per hour, but we're looking for 20 per hour. So even before you start a problem, if you think, and you can do process of elimination and get rid of large probabilities. Agree? So find the probability that at least 1 salmon swims upstream. We need CDF for that. So I'm just going to wait. I love to do it the algebraic way with the PMF and all, but since you have a calculator, just use the calculator. So the first one, call it XA, it's Poisson lambda A. So in this case, I'm assuming t equals 1 hour. So lambda A is 10. So lambda A simply means 10 per hour. If we go back to our notation, lambda t would be equal to 10, right, at t equals 1. So Poisson 10, t equals 1 hour. We want to find the probability XA equals 20. You can use your calculator, it has Poisson PDF. Lambda followed by X 20. And what is that value? 0.0019. As expected, it is a very small probability. A, want to find the probability that at least one salmon swims upstream in river B in 10 minutes. So this is where the lambda t kind of plays a good role in finding the probability easily. So I know XB is Poisson, is it 8? Yeah, 8 per hour. So if we want to look in terms of minutes, I'll just call it XBM, which stands for minutes. All I have to do is take lambda, which is 8, and multiply it by time. So lambda B is defined per hour. So in this case, it has to be 10 minutes, right? 10 out of 60. Yes, so the original Poisson is 8, and the per minute Poisson is simply 8 multiplied by 10 over 60. It's 1/6 and 4/5. Good. Some of you made a mistake here. Now, Poisson would result in an infinite sum, so you need a calculator. But the calculator, anytime it computes CDF, it's going to give you a less than or equal to probability, because by definition, cumulative distribution function is always for x less than or equal to x, right? Always less than or equal to x. That's how we define a CDF. So in this case, we want a less than or equal to, but the probability that we're trying to find is greater than or equal to 1. Yes.
Could you do it without just summing to infinity and seeing if the series converges?
The series will converge.
Okay. Like
Yeah.
You just have to figure out
How to do it.
So it just sucks to do it all.
Yeah.
Okay.
So it will converge, but it's painful.
Gotcha.
If you love pain, go for it. So greater than or equal to 1, the complement of that is 1 minus the probability of x is less than 1. Based on the support, we're doing it for Bm per minute. So 1 minus the probability, there is only one value. Yes. And do we need a CDF for that? We can use a CDF, but it's an exact probability, so Poisson PDF. The lambda is 4/3. 0, and what do we get?
0.736.
That's the final answer. After.
Yes, oh, sorry, 0.261 minus 0.264.
So 0.736, one more decimal.
4.
And the last one, you want to find the probability that at least 3 salmon swim upstream in all 3 rivers combined during a randomly chosen 1 minute interval. So we're looking, what happens in 1 minute. So XA is Poisson 10. Using the same strategy that we did in the previous case, XAM will be Poisson 10/60. XB is Poisson 8. So per minute, Poisson 8/60. XC is Poisson 16. XCN, same strategy, Poisson 16/60. Entire purpose of this problem is to reinforce the fact, since they are independent, I'm calling it 3 different rivers, A, B, and C. Suppose you had a problem where I said, okay, you have the same river A, and then you partition that river, you have the right side of the river, the left side of the river, and you try to do a Poisson there, it's not going to be independent because it's the same river. Does that make sense? So independence is key. So since we are combining all 3 of them, that has to be Poisson 10 plus 8 plus 16, 34, 34 over 16, 17 over 30. Good. We want to find the probability that y is greater than or equal to 3. At least 3. The complement of that is 1 minus the probability of x less than 3. X less than 3 is equivalent to saying 1 minus the probability of x less than or equal to 2.
Yeah.
Right. Why are we doing this? Because we're trying to get back to the definition of CDF, and that's what the calculator is going to do. So 1 minus Poisson CDF, 17 over 30, comma 2, and what do we get?
0, 2, 0, 0, which you told me was wrong.
0.01.
995. That's what they get.
But if you round it to 4 decimal places, that's.
Okay, did I say you should round?
Okay, then list the entire string, infinite string.
I agree, but 0.01995. If you round it, it's 0.022%. Does that make sense though? Why cannot, I mean, at least 3. I mean, 10 per hour, 8 per hour, 16 per hour.
Yeah.
Why is that a small probability? Because it's per minute, not per hour.
Yeah.
Does that make sense?